as I mentioned, this week, what we will do is we will look at coagulation, and we'll do somewhat of a little bit of a review initially with a poll question, and then we'll work through a problem. We won't finish the entire problem today. And I'm going to summarize it, add a little bit more on Wednesday and a little bit more on Friday. And I will post all of the videos. I do not know why the poll is not working, but the poll question is on your screen. So we'll just call this A, B, and C. A for sodium chloride, B for calcium hydroxide, and C for aluminum sulfate or alum. It looks like C wins, and that is correct. And the reason it's correct is shown in this figure here, okay? If you've watched the video, in there I explain about the stern layer and the double layer. So that this first layer here is referred to as the stern layer, and kind of it's referred to as a fixed charge. Kind of think about it is if you could put a little string on that layer and pull it, it would pull, and the charge would, the ions would move with it. And then we have the double layer, more diffuse concentration of ions that are somewhat associated with the particle itself. And what is shown in the diagram here, switch to the highlighter. So what's shown here is we can, some mornings things don't quite work. Okay, so what you can see is this diffuse layer, this potential, if we're measuring the potential at the particle, the potential is greater at a greater distance away from the particle. So this diffuse layer right here is essentially thicker in a solution with sodium chloride. And you can see, okay, as we get closer, so if we took, let's take 10, and what we can see then is the distance out is much greater. And the importance of that is that here's our, I can write on this side, but I can't write over there. Don't ask me why. Okay, so we have these particles, and often our clay particles are negatively charged. If they're negatively charged, when two particles come together, they repel. But if we increase the charge of the coagulant that we add, that decreases this distance here, allows those particles to approach one another better, or closer, really, not better, but closer, so that the attractive forces can overcome the repulsive forces. Therefore, the two particles stick together, they grow in size, and they're heavy enough to be removed by sedimentation. So that's really what's happening here. And you can see that, again, in this diagram here, we're plotting residual turbidity. We want to look at this diagram here, and you see the amount of coagulant that we need decreases by several orders of magnitude if we move from sodium to calcium to aluminum. So that's an important finding. That's important. It's important to understand that, and this is why we typically will use alum, aluminum 3+, ferric, Fe3+ as our coagulants. We can decrease the dosage significantly. Problem that I want you to think about first is we have a situation where we have a surface water treated for removal of color and turbidity. It's a conventional surface water treatment plant, uses coagulation, and the coagulant is ferric chloride. Also uses dual media sand filtration with disinfection by chlorine. So we have a lake, pumping water from the lake. Typically, we would pump it from deep in the lake so that we have a more constant flow concentration, of various contaminants, chemicals in the lake, along with a constant temperature. And that is beneficial in terms of treatment. Typically, that water flows first through a screen, then through rapid mix, and it's in the rapid mix basin that we're adding our coagulant. So that's the ferric chloride here. From there, the water flows into a flocculation basin. Typically there, we have much slower mixing. We want to allow the particles to contact one another and aggregate and grow in size. Now that we have particles that are sufficient size that they will settle out, we then treat that water with sedimentation. Water then sludge settles, and the water flows then into our dual media filtration system. We do produce some residual from that. We actually produce backwash water because we need to remove the particles that are caught in the filter in order to prevent significant clogging. We'll talk about that later. And then the water flows into typically a disinfection chamber, and then would flow into a storage basin and be distributed. So we have a plant that's treating water. We have a maximum daily flow rate of 0.88 cubic meters per second, or 20 million gallons per day. The optimal ferric chloride dose was found to be 21 milligrams per liter, and the average suspended solids concentration in the lake is 32 milligrams per liter. The effluent suspended solids concentration from the sedimentation basin is 1.5 milligrams per liter. Now note, when we're looking at the amount of ferric hydroxide produced, it is produced at a 1-to-1 stoichiometric ratio with the ferric chloride, and that is independent of whether or not we have alkalinity or we don't. Okay, the first thing we were asked to do was to determine the mass of ferric chloride required per day, and we are told that we have 21 milligram per liter as our dose, so that was the optimal dose. If we multiply that by 0.88 meters per second, so our maximum flow rate, times 1,000 liters per cubic meter, similar to what we, times 86,400 seconds per day. That's a number that's useful to remember because you will use it extensively, times 1,000 milligrams per gram, and 1,000 grams per kilogram. Grams cancel, milligrams cancel, and we would need about 1,600 kilograms per day of ferric chloride. Now, I didn't ask you this, but ferric chloride is actually provided as a liquid. And it's about 35% by weight is how it would be purchased. So since it's by weight, we need to actually divide that by 0.35. And the solution that we would be buying would actually weigh 4,562 kilograms per day because it's only roughly a third pure. The density of that 35% solution is equal to 1,183 kilograms per meter cubed. So in order to determine the volume that we would be purchasing, we need to divide by the density, and that is equal to almost 4 cubic meters per day of solution. And just to give you a sense, that is roughly about 1,000 gallons per day of ferric chloride solution that we would be purchasing. So let's look at calculating the concentration of both the suspended solid sludge and the ferric hydroxide sludge. So we started with 32 milligrams per liter, subtract 1.5 milligrams per liter. We're going to multiply that by the flow rate, multiply by 1,000 liters per cubic meter by 86,400 seconds per day. So seconds cancel. Notice liters cancel, meters cubed cancel. We now have milligrams per day. There are 10 to the 6 milligrams per kilogram. And that is equal to 2,320 kilograms per day. Now, we said that we had 21 milligrams per liter of ferric chloride that we're adding. We need to determine the amount of ferric hydroxide sludge that's produced. We can divide that by the molecular weight, and that is equal to 0.129 millimoles per liter. So we get a 1-to-1 stoichiometric ratio. So we take 0.129 millimoles per liter. Now that is the ferric hydroxide. Remember, we have 3 waters of hydration. We will multiply that by 160.92 milligrams per millimole. It's the molecular weight of ferric hydroxide that includes the 3 waters of hydration. And that is equal to 20.83 milligrams per liter. Again, to essentially the same calculation we did above, we have 20.83 milligrams per liter. Again, multiplied by 0.88 meters cubed per second times 1,000 liters per cubic meter. Again, liters cancel, meters cubed cancel, times 86,400 seconds per day. Seconds cancel, times 1 over 10 to the 6 milligrams per kilogram. Milligrams cancel, and that is equal to 1,584 kilograms per day. Notice this is dry weight. And if we add those, that is 23.19, or rounded to 2,320 kilograms per day, plus the 1,584 kilograms per day, and that is equal to 3,904 kilograms per day. That is the dry weight of sludge that is produced.